molarity, now we've got to take a step into another type of reaction in terms of, it's not a reaction, it's a process, and it's a dilution. And this, you do not use dilution when you're doing stoichiometry. You use dilution when you see the word dilution, water is added, stronger concentration to weaker concentration, any of those things. But usually look for water being added one way or another, or the word diluted in the statement. If water is added to the solution, it is diluted. We say the solution is diluted. The original solution is concentrated, and it's concentrated because it has more in it. After the addition of water, the solution is said to be diluted. Again, same thing with your orange juice that you buy at the store in the little containers, then you dilute them. And the trick to this is that the moles in the concentrated are going to be identical to the moles in the dilute. Because remember, you're adding water, which is the solvent. You're not changing the amount of solute. Since moles come from molarity times volume, because remember, molarity is moles per volume. So if you take molarity, which is moles per volume, and cancel the volume, you're left with moles. So because of that, and because the moles of the concentrated are exactly the same as the moles in the dilute, then what you end up with is the moles of the concentrated equals the moles of the dilute, because this is equal to moles. Now, an easy way to do this is MCVC is equal to MDVD, or this is simpler, M1V1 is equal to M2V2. Okay, this is a dilution, and what this does is it doesn't matter what your concentration is or your volume is, as long as this volume matches this volume and this concentration matches this concentration unit-wise. So you could use liters, you could use milliliters. You don't have to convert it to liters, because if you convert milliliters to liters on one side and do it on the other side, it cancels itself out. So we just need the units to be the same. This brings me to when you do the spectroscopy lab, and you'll do the spectroscopy lab later in the in the semester. You'll have a series of dilutions, and it's called where you use the previous solution to make the next one. So you use an original solution to make the first one, then the first one to make the second one to third one, and on down the row. And it's called a serial dilution because you're doing the same thing over and over using the previous one. All right, so how do we work a problem? Okay, to prepare 325 milliliters of 2 molar from concentrated, how many milliliters of concentrated acid is needed? Well, M1V1 is equal to M2V2. So the trick is to keep your 1's together and your 2's together. If we designate this one V1, then this has to be M1. And this one is M2. Now we could have designated the first one 2. It doesn't matter which way you call them. So that being the case, we're going to take 2.0 molar times 325 milliliters is equal to 16.0 molar times X, because what you're looking for is the milliliters you need for the process to occur. So if we set this up, X is equal to 2.0 times 325 milliliters molar divided by 16.0 molar, you're going to get 40.625 milliliters. If we look at it, we have 3 significant figures, 3 significant figures, and 3 significant figures, so we'll report it as 3 significant figures. 40.6 milliliters. So you would take 40.6 milliliters of the concentrated and dilute it to 325 milliliters, and you would have the solution you need. Okay. 2, a laboratory procedure calls for 75 mils of 125. So V1 is 75.0 milliliters. M1 is 0.150 molar. You have available 225 milliliters of 0.85. So that's what you need. What you have is 0.85 molar here, volume 2. Do you put the 225 in? No, for 2 reasons. One, it's more than what you need. And B, it's just sitting on a shelf, and that just tells you what you have. So if you need less than 225 mils, you have it. If you needed 300 mils, you don't have enough to run this. So we have to have our unknown, so that's our unknown, or X. So M1 V1 is equal to M2 V2. Now in the first one, I set it up, so substituted it, and ran it. In this one, I'm looking for V2, so I'm going to go ahead and rearrange it. So M1 V1 over M2. So then I'll plug it in, 75 milliliters times 0.150 molar divided by 0.85 molar will give us, run it through our handy dandy little calculators, and we get 13.23529 milliliters. If we look at it, 75, this is 3 significant figures, 3 significant figures, and 2 significant figures. So we report it as 2 significant figures, so it's 13 milliliters. Now, which way works better? Whichever way makes you happy. Both of them do the same thing. I like to rearrange variables. A lot of people like to work with the numbers once they've got them in. Describe how you would prepare the solution of 0.05 liters of that from 0.125 molar solution. Okay, so this is V1. This is M1. So this is M2. So what we need initially is V2. So M1 V1 is equal to M2 V2. So V2 is going to be equal to M1 V1 over M2, which is equal to 0.085 liters times 0.0500 molar divided by 0.125 molar. Okay, we run the math and we get 23.4375 milliliters. 3 significant figures is 23.4 milliliters. So the question actually said, describe how you would do this. You're going to take 23.4 milliliters of the 0.125 molar solution and dilute with water to a volume of 85 milliliters. Now, you could have done all that using liters, and that would have been fine. It does not change the values as long as your units are the same. You either use both moles or both liters, both milliliters. As long as your M's equal and your V's equal, it doesn't matter. Okay. So now we've done concentration, molarity. Now we've added solvent to it and see what happens. And next we will take it back to stoichiometry.